All right, we're back to 2.3 again. We're working through some limit examples. And we want to see how to algebraically compute a limit. So if you're trying to compute the limit as x approaches a of f of x, right, there's some things that you should try first. So can you directly substitute x equals a? If you can, then you should do it. Typically, when we say you can't, that means you probably have something like 0 divided by 0, and so you have to do more work. And so you could also use a limit law. In fact, these are kind of the same thing for some functions, right? Because if we have a polynomial or a rational function, we know a limit law says that you can directly substitute. 3, we should try to simplify where possible. Simplify first if you need to. We're going to see an example of that in just a second. 4, factor and cancel. That's a very popular one, factor and cancel. 5 will be multiply by a conjugate. Oh geez, I ran out of ink on my second pen. Good. We're going to see an example of these in just a second. Let's just go ahead and try one maybe. I'll just kind of hold off there. So limit as x approaches 0 of the square root of 3 plus x minus the square root of 3 divided by x. Okay. Now the first thing you do is try to directly substitute. Can I put in x equals 0? If I do, I get square root of 3 minus the square root of 3, which is 0, divided by 0. So this is a situation where we have 0 divided by 0, so I can't do that. Now, what I would like to do, if I see a square root sign, multiply by a conjugate is kind of a nice thing to try. And the reason is because a little bit of review here over on the side. If I have a plus b times a minus b, do you remember what that is from algebra? Oops. That's going to be a squared minus b squared. And so notice what happens here, right? If I have, if my a is like the square root of 3 plus x, then taking a plus b times a minus b is going to get rid of the square root. And so this expression won't have square roots anymore. And so the idea here is I'll multiply by the conjugate to see if I get anything good. Okay, so the numerator becomes something nice by design, right? So that's going to be the square root of 3 plus x squared, which will just be 3 plus x. And then we have minus the square root of 3 squared, which is just 3. Now you could multiply this out if you wanted to, but because we have this rule right here, I'm just going to use it directly. And then divided by x times the square root of 3 plus x plus the square root of 3. Good. And now the 3's cancel. So I'm having x over x over square root of 3 plus x, blah, 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 blah. Very good. Okay, these are all factors now, so we can cancel the common factors. And we're left with 1 over the square root of 3 plus x plus the square root of 3. And at this point, you can see that you can plug in 0 now. And if you plug in 0, you get 1 divided by square root of 3 plus the square root of 3. That is 2 square roots of 3. Good. So there's the limit. All right. I kind of went sideways on you. So this is an example where we're multiplying by a conjugate in order to simplify the expression first. So we have to do something before we can simplify. Good? All right. Let's try another one. How about something like the limit? Whoops. Can you see? Where am I? Limit as x approaches. How about t approaches 0 of 1 over t minus 1 over t squared plus 1. Now, notice that I can't just put in t equals 0, right? Because that's like infinity minus 1. Oh, that doesn't seem like there is a limit. Oops. I see I forgot a expression. That's t squared plus t there. How's that going to work? Well, first of all, notice that this is t times t plus 1, right? And so I'm thinking about my list over here. Is there anything I can do? And I think number 3 is where I'm going to go. I'm going to try to simplify this first by creating a single fraction. And so if I create a single fraction, my common denominator is t times t plus 1. So for this fraction, I'll need a t plus 1 over t plus 1, right? And so that will be the limit as t goes to 0 of t plus 1 minus 1 divided by t times t plus 1. Oh, that's nice. The ones cancel, and what do you see? Something beautiful is about to occur. The t over t plus 1, the bad point goes away, and you're left with 1. Nice. I love these textbook problems. They're beautiful. Beautiful problems. Okay, so I think we now have had examples of each of these situations. So I think what's next is we're going to talk about the thing that I delayed the last time, and that is the squeeze theorem. Sorry about the squeaky chair. Squeeze theorem. So what's the big idea behind the squeeze theorem? Graphically, I think it's pretty easy to see. So I've got some function f. Let f of x be less than or equal to g of x for, let's just say, all x. Okay, so therefore the function f is going to be, like that. There's my f. And then I need another function g that's always less than that. And I'm doing this because the second condition is, okay, I can write it like this. It's a little bit different, but I'm going to take that the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x is equal to L. And so L is the y value over here. Good. Now, let h, let's see, let h of x be squeezed between f of x and g of x for all x. Then our conclusion is going to be, what is the limit as x approaches a of h of x? So in other words, h of x is anywhere inside between these two functions. So this is my h of x. And if I take the limit as x approaches a of f of x, of h of x, what do I know has to happen? Well, f and g are squeezing h together. And so at the point x equals a, f equals g, and so that forces h to also be the same thing. And so the limit for h is equal to, that's an h of x, by the way, here, is also equal to L. Good. So that's known as the squeeze theorem. Now, to use the squeeze theorem, typically the hard thing is to find the upper and lower functions. And so that's typically, I keep saying typically, but it can be kind of a hard thing to do. Let's take a look at an example. X going to 0. Let's say X squared sine 1 over x. Well, how is this going to work? Well, the sine function is always the sine of anything. The sine of anything, right, is going to be stuck between plus and minus 1. And so this is actually giving me the upper function and the lower function. So in other words, I know that x squared times the sine of 1 over x is going to be less than or equal to minus x squared. Oh, sorry, plus x squared. And less than or equal they're going to have, this is going to be squeezed between plus and minus x squared. So therefore, here's my x squared, here's my minus x squared. So the sine of 1 over x is waving around in here. And so we see here that the limit as x approaches 0 of x squared sine of 1 over x is going to be the same as the limit of x squared and minus x squared, which is 0 by Squeeze theorem. Okay, I'm going to stop there for now, and maybe we'll try one more example of the Squeeze theorem.